Everybody got a packet? All right, this is a little bit of a hodgepodge unit. There isn't really any continuity here. These are just kind of two topics that we didn't really know where else to put them, so we put them together now. It's not necessarily like one thing has anything to do with the other, and that's piecewise functions and geometric series. We have 3 days to be able to cover each. I don't know how it's gonna go. Maybe it goes by faster, but some other things I have penciled in are for Wednesday to give you back the test that we took 2 weeks ago, but I still have 4 people that haven't taken. But it's 4 people that hardly ever show up, so if they haven't shown up by Wednesday, then I'll probably just give it back to you, and they can keep their 0. It's we took that test not last week, the week before, so. Zeke, are you cold? Oh. But you're having a really nice hair day, man. You should show it off. There you go. That's nice. And if we can start making pretty good pace through this packet, I don't mind taking you to the lab on Friday maybe. But we'll see how it goes. I haven't booked it yet, put it that way. And then if I see that we're doing well this week, then I will. We don't have any assessment this week. There's no test or quiz. The next quiz is next Tuesday, the March 3rd. So you don't have to worry about any assessments this week. Any questions for moi? Yes, sir. I want to say it's on con, but I'm not sure. You'd have to look it up. Speaking of homework, the homework grade for last week is in already. You'll see it tomorrow. It's con? There you go. Julian just answered your question. Yeah, March the 1st is March 1. What day is it before March 1st? No. It's not. No. 29th is a leap year, yeah. It's a leap year. Every election year and every Olympics year, it's a leap year. Facts. Saturday. No, it's not a World Cup year. It's Olympics and election. All right, so let's try to get through this. Let's see if we can match first period, even though they were half asleep. Let's see if we can get as far as they did. The first, so I said it's kind of a hodgepodge unit. It's not necessarily that it's all related and stuff. But the first part, piecewise functions. We're still dealing with functions, so we still have to abide by like a vertical line test and stuff. But now the functions can come in pieces. They may lack continuity. Okay, like so for instance, this example that's here, I know you can't see it on your paper, but whatever, it has 3 pieces. And the way that that's accomplished is by breaking up the outputs along intervals. So, like maybe here we can look at it like this. I know interval was a big word for you guys before. Some of you missed what does the interval relate to directly? The domain, all right? So what will happen is, here we'll have a function and it will equal, but it can equal different things depending on where we are in the domain. They'll give you different intervals along the domain, and every different interval will give you a different output. Okay? Now, the method that we're going to use when it comes to graph, it's going to eliminate the need for you to remember how to graph these. Typically, really, we graph via transformations. Like even going back to lines, right? How did you graph lines? Well, with a slope and a y-intercept, that's kind of like using transformations. Even though you didn't know it at the time, it's kind of like using transformations. When we graph parabolas, we use transformations, A, H, and K. When we graph the radicals recently, A, C, H, and K. We tend to graph with transformations, but I'm gonna just knock that out because I think we're gonna it'll make life more difficult. But just for fun, this is a nice example to have here, because if we look at all three outputs, they're all different. So see, let's go one by one. Can you give me a word that would describe that output? Like what type of function is that? Quadratic, yeah, that's a quadratic function. It would look like a parabola, but it's only going to look like a parabola when x is less than 2. What's a name for this type of a function? Notice how there's no x in there. It's a constant function. Very good. What does a constant function look like? Not just a line. Remember, if f of x means the same thing as y, Landon, if I were to just say y equals 6, what would that look like? You saw this with asymptotes. It'd be a horizontal line. Those are the ones you're going to like the best. And then over here, even though this we have the x after the constant, but what would be a word for that? Linear, yeah, that would be a diagonal line with a slope of -1 and a y-intercept at 10. But the thing is, it's only going to look like that within that interval. So I included this as part of your notes because I wanted it. I didn't like the explanation stuff that was already in the packet that some of the teachers used, but then it ended up printing out too small. So I'm not going to go over every single thing. I'm only going to go over some of the highlights. So like here's an example, right? Here we have a function h of x. And when it's less than or equal to 1, and this is an important thing, what is that? When you go back to when we graphed inequalities in Algebra 1, okay, what does that or equal to sign mean underneath the well, it means that at that point, yes, it does mean that it can be 1, but it means that as far as the graph goes, like if you go back to inequalities, that at that point, you would fill in the point. It wouldn't be empty. That's going to be important. So if you look at the graph of this, h of x gives me an output of just 2, which we said is a constant, and it goes from 1. So notice how here we have a closed point at 1, 2, but it's only going to be a horizontal line when we're less than or equal to 1. So even though you can't see an arrow, that arrow is going that way. Okay. Then this h of x is going to give me an output of x. So if you always want to put in these endpoints. You always want to see the endpoints of the interval to see what it's going to be defined at. If I plug in a 1 for x, what do I get back out? If I say y equals x, because that's what that means, and I put in a 1 for x, what am I going to get for y? Also a 1. But because this is not included, it's not equal to, it takes an open point there, and then you'd also get the points 2, 2, 3, 3, 4, 4, which gives you the look of a line going that way. We'll do plenty of examples today. If it's not making sense right away, hopefully it will by the end. Yes, sir. I'm putting a 1 in for x, just to see what the y gives me. Okay. So notice how both of these intervals here have a 1, right? But only this has the or equal to sign. So in order to be a function, if I were to get a vertical line and pass it through the entire function, I'd only be allowed to touch it once. If not, it wouldn't. Stop it. Come on. No. Nope. Come on. Come on. Let's try again. There you go. I'd only be able to touch it once. So here at 1, okay, this open point, which is part of the second interval here, means that 1, like this point is not included in the function. The one that is the one up here. And the reason why is because 1 was part of that interval. No, it could be above it. You just can't have 2, because if you were to have 2 closed points, you'd fail the vertical line test. It would touch it twice. There's going to be somewhere there'll be gaps. There's going to be somewhere, you'll have a closed point here and something going that way, and then the next point will be over there. And who knows, maybe it could even be closed. It's just going to be different little pieces. That's why they call it a piecewise function. The other thing that's important is knowing how to evaluate functions. So there's two main parts of piecewise. Graphing a piecewise and evaluating a piecewise, where they're going to give you inputs, but you have to know not only how to how to find an output, but where to put the input. So here they go into this whole thing about a doctor's office and how much a doctor charges. Now the good thing is you don't have to model this. They've already modeled it for you. They've taken these fees and they've given you already a piecewise function for it. They tell you how much that the doctor charges based on how long you're there for, how much of the time you're taking up, which is kind of a weird thing. I haven't seen a doctor that does that, but okay. So let's look at the questions. How much would they charge for 12 minutes? Well, the first thing I want to do is, since minutes are the input, I want to see which one of these pieces would I have to put that 12 into. So where on the T's, minutes is the type of time, and let's just call it the first piece, second piece, third piece, what piece would that 12 go into? First piece, second piece, or third piece? The second piece, because 12 minutes is in between 6 and 15. Another way to write what they did there with saying t is greater than 6 and less than or equal to 15 is to say 6 less than or equal to time. Sorry, 6 less than time less than or equal to 15. It's another way of writing it. It's saying that the t is in between there. 6 is in between 6 and 15. And when you put in a 12, what's the output? Just 80. There's no variable there. It's just 80. That's why it says 80 there, even if you can't see it on your paper. How about 20? If I were to take 20 minutes at the doctor, what would they charge me? Or better yet, what piece would it go into? The last piece, right? Because now you're spending more than 15 minutes there. Well, it looks like there we would have some operations to do. So it would be 80 plus 5 times 20 minus 15. That would be this function evaluated at 20. So that would be 80 plus 5 times 5. 5 times 5 is 25, so that would give me 105. If you can see, that's what they tell you they charge there, 105. Absolute value functions, which look like a V, we'll do those later in the year. That you could learn them as a piecewise, but we'll do those later. We're going to use transformations. So the main type of So think of piecewise like as an umbrella term. Anytime you're breaking your function into pieces, we call it a piecewise. But the main type within piecewise, the main type we're going to do, I don't know why they call it a floor, but if you're paying attention, change this. We're going to refer to this as a step function. Why do you think they call these, look at the picture, why do you think they call it a step function? They literally look like steps. They look like if somebody is climbing up a set of stairs, right? Well, a step function would be one where all of the outputs are just constants. If there's no variables in the outputs, if they're just giving you numbers, that would just be horizontal line, horizontal line, horizontal line. We call those step functions. Those are going to be the ones you like the best because they're the easiest to graph and they're the easiest to evaluate. You don't have to do any operations. Again, I don't know why they call it a floor function here. Let's call it a step function. All right. Speaking of step functions, here's a step function. Look at all of these. There's 4 pieces here, but look at all of the outputs. What are all of the outputs? Sophie, didn't we make a deal? Okay. So hold up your end of the deal. They're all constants. Okay. Also notice how I've been using the word output. Here they wrote the word rule. Just in case you see the word rule, just think of it as the same as output. Where I've been using the word interval, they've been using the word domain, but that should be a little bit more intuitive because we know that intervals deal with domain. Let's practice evaluating each of these outputs. Okay, what would be this piecewise function? We have all these little pieces. What would be the function evaluated at -5? Well, first you got to figure out which piece that -5 would fit into, and then tell me what would come out of it. It would be -4 because -5 is part of this first piece. Now, here's another thing. Let's say they give you an input that doesn't have anywhere to plug in. Like, let's just say instead of a less than or equal to sign, let's say this would have just been a less than sign. Well, there's no place that -5 would fit into. What would be the output? It'd be undefined. It'd be like an error. But because that has an or equal to sign, there is a place to plug it into, and really we're not even plugging in because it's just a constant. But our output is a -4. Landon, you look hyper-focused today, man. If today was a game day, you'd score 30. Here, Landon, give me the next one. How about -3? Not sure. Not focused enough. These are the good ones. Like, if you're going to make a mistake, it's going to be on these. Because when you look at the domain, you look at the intervals. Well, geez, -3 is included on 2 of them. But what's the difference? Yeah, only the second one has that or equal to sign. So that means that -3 would fall in the second piece. What's the output there? -1. Landon, you want to try to redeem yourself with the next one? -1? No? Go ahead, Jenny Fan. Very good. That -1 would fit into this piece because -1 falls in between -3 and 0, which gives me an output of -1. Miles, do you want to try the next one? What's the output for 0? It would be 2, sure, because even though we have 2 different zeros here, only the second, which is part of the third piece, only that one has the or equal to sign. So that would give me a 2. Good. Sid, the next one. Nope. Yep, 2.5 falls in between 0 and 3, which gives me an output of 2. Since 2.5 falls in this interval, my output is 2. It doesn't matter. It could be wherever. If this would have been less than and this would have been less than or equal to, then it would have been -1. They can't. Well, it depends. They cannot both be or equal to, because then it wouldn't be a function. Okay. Now they could. It actually could both be this, and then what would be the case there for the 0 if they were both a less than? It would be undefined, sure, because then there would be no definition at 0. The function would not be defined at 0, which is kind of the same thing as no solution. Lauren, you want to try the next one? 3. Very good. Take that, Sid. And then my homie Yosh, who I haven't called on yet today, what is this function defined at 4? Very good. 4 fits into here. This gives me a 5. Muchas gracias. All right, domain and range. So here we have some graphs. Like we're going to start graphing ourselves now, but here we've got some graphs. Let's see if we can identify the domain and range. It gets a little bit tricky because now there's discontinuities. These graphs aren't continuous, so you might have some gaps. Let's start off with the domain of this first one. How far left does this go? It does. We do have this branch going to -infinity. Anytime you have an infinity, it's a parentheses. And even though as we go to the left, we clearly get into a different branch, from piece 1 to piece 2, it's continuous because we have a solid point, and then we just, it's a different piece, but there's never a discontinuity there. Okay, so when's the first point that we reach a discontinuity? Well, yeah, it would be 2, and now the thing is, you'd be like, oh yeah, because look, look at this gap. But that gap has to do with the range, not with the domain. The only reason why there's going to be a discontinuity at 2 is because here we have an open dot and there we have an open dot. This graph has no, if I were to ask you to evaluate this at 2, it would be undefined. There's no output there. So we're going to put a 2 and we're going to put a parentheses because there's no output there. It's not part of it. But there is definition to the right of 2, so we'd have to do a union. Where would we start the second interval? 2 again. Until when? Up until positive infinity. There's an arrow there. It's just hard to see, but it's there. Yeah. No, we're over here. We're still in the green part. Now, a lot of times these things won't have arrows because it got cut out of the picture. But as long as I don't see like a point there, I just assume that it would go on forever. But this one actually does have an arrow there. There's a green arrow. It's just hard to see. Okay, how about range? Range is how low to how high. How low does this go? It does go as low as -2, and we actually do touch -2, so this is going to take a bracket. Then on the way up, we do not go all the way to positive infinity because there's clearly a gap here, right? So on the way up, we need to stop where? At +2. Does that 2 take a bracket or a parentheses? Well, you would think parentheses because of this, but look, it's defined over here. There are some outputs, so it would also take a bracket. Union. How about the second piece? Or where do we start off again? At 4, bracket or parentheses? Yeah, it is parentheses because there's nothing at 4, just that open dot. So it would be at 4 up until positive infinity. All the infinities always take parentheses. Let's try this next one here. Domain. How far left do we go? -4. Bracket or parentheses? Bracket. Good. Up until when? What? But there's a gap here. Yeah, but look, it's defined. If this would have been 2 open dots, yeah, then I'd have to cut off the domain and then restart it. But there are no discontinuities here. If I were to ask you to evaluate what is this function at 3, what would the output be? It'd be 3 because here I have a closed dot. And then it just starts up on the other end. How about the range? How low do we go? -4, bracket again. How high do we go? We do go up to 4, but parentheses. Because even though it cuts off here with we still have this part of it taking this up. But then that open dot makes it a parentheses. Yes, ma'am. Where did the 7 come from? From here. We go as far right as 7. If I were, look, let's take that same vertical line that we had earlier, Hannah. Vertical line, right? And I were to tell you, hey, what is this function at -2? Could you give me an output? Yeah, it's at -2. If I were to tell you, hey, what's the output at 1? Like, you could always give me an output, The only time it gets a little bit sketchy is right here at 3. Because at 3, you're like, oh man, is there an output? But yeah, there is, because there's a dot there. The output would also be 3. And the second I just inch over a little bit, like let's say I were to go to 3.5, is there an output there? Sure, yeah, I'm on the next piece, but there's an output. It looks like it's 3. And I can continue to give you an output. The only place I would where I would stop eventually being able to give you an output is once I get beyond 7. No questions there? All right. Uh, this just tells you about step functions, which we already talked about. Step functions are just made up of a group of constant functions. And let's try to get through these next two slides, and that would keep us on pace with first period. Here we're going to not only graph, but then they're also going to ask us to either evaluate, find domain and range, and then one more thing, which I'll show you when we get there. Okay, let's first evaluate. Sid, let's redeem ourselves. What is this function evaluated at an input of -2? Okay, well, very well. The -2, being that it's less than 0, is going to be put into x squared, so that would be good. And this was sadly evident on the performance final, that some of you still don't know how to square a negative. I don't know. Like, I mean, this happens to be -2 squared, but let's just say maybe we had like a -7 squared or something like that. Like, what happens when you square a negative? Yeah, get a positive. So -2 squared is 4. Ali, how about f at 3? Anybody could be wrong. It is going to be in the second one. And I'm going to put that 3 into 3x, so it would be 3 times 3, which would give me an output of 9. These are all points I can put on when I graph. And then Emily, how about f at 0? No, well, since at 0, this is contained in here, it would be 3 times 0, but you would get lucky even if you pick the wrong one, because 3 times 0 is the same thing as 0 squared. Okay, now it's time to graph. What word can you use to describe that piece? Quadratic, so you're expecting that piece to look like a parabola. What can you use to describe that piece? Linear. You're always going to want to see what's going on at the endpoints. So, like, for instance, let's do the first one, x squared, right? So let's do x, and then let's do x, and then let's see what's going on at x squared. I want to put in a 0 because that's one of the endpoints. What's 0 squared? 0. Now, for the rest of the inputs, I have to abide by the interval. The interval for that is numbers that are less than 0. So what are some numbers less than 0? Yeah, now for parabolas, I used to ask for 5 points. One of them was the vertex, which I guess here we got lucky. The vertex is at 0, 0, but I think if you do 3, that should be enough. So -1, -2. Let's do another one. Let's do -3 also. So this -1 squared is 1, -2 squared is 4. This gives me 9. Let's look at the next one. I want to see what's going on here, so I'm going to put a 0 in. What are some other points that are part of that interval? Positives, yeah. So now, what word could I use to describe that? What word can I use to describe this type of function? It's a line. So really, what's the least amount of points I need in order for a line? 2, yeah. I know we didn't have Algebra 1 together, but in Algebra 1 I used to ask for 3, but 2, all you really need are 2, so you don't even need all those points, just 2 and then connect the dots. So I know this is going to be 0, and just pick any other point, like let's say this is going to be 9, and just connect those dots. So when we go to the first one, now look, see this 0 that I put in here was not inclusive, so when I put a 0, 0, it's supposed to be open. But now I go -1, 1, negative 2, 4, negative 3, 9, and I make it look kind of like a parabola. But now this 0, which just happened to also give me a 0, was inclusive, so I get to now fill in that point because it just happened to be at the same spot. It's just a coincidence. It's not always going to happen like that. It's a coincidence. And then I could have picked several more points, but all I really need are just one. All I need is one more. I picked 3, 9. And since I know it's going to be a line, I put a point at 3, 9. And that's a straight line. That should be crossing through 3 and 6, like 1, 3, and 2, 6, because that's also part of it. You could also argue that this has a slope of 3. It's going up 3, right 1, up 3, right 1. Right 1? Cool. And even though they're not asking us just for fun, let's do domain and range here. Let's get some more practice with domain and range. What's the domain here? From left to right, there are no discontinuities. This is defined everywhere. We have an arrow going forever left. We have an arrow going forever right. There are no gaps in between. So my domain is all real numbers, negative infinity to positive infinity. How about my range? Bracket 0, because it does touch 0. It just doesn't go any lower than that. Look at Emily. Good job, Emily. Bad job, Thomas. Where were you on that one? No, you're not. You're not sleeping. Any questions? All right. Let's go to example 2. What word could we use to describe this? That's linear. What word can we use to describe the second one? We graph those. Square root. Yeah, somebody said radical, find it, but it's a square root. Now, we're not going to use transformations like we did at the beginning of the semester for these. We're just going to use input and output. Here, they're not asking us to evaluate. They're asking us for domain and range, but let's graph it first. How many points do we need in order to graph a line? Really, just 2. Now, I want to make sure I get the endpoint in there. So for this first one, I want to put a 4, but then if you put one more point, make sure that it's less, it falls in the interval, which is less than 4. Give me another point to put in. I like 0. I'm going to put 0. 4 minus 4 is 0. 0 minus 4 is negative 4. So let's put those 2 points. Now, at that 4 here, is it going to be open or closed? It's going to be open. So at 4, 0, I got to put an open point because it was a less than sign. And then at 0, negative 4, there I can put it closed. I know it's just a line. So there you go. For square roots, how many points will we ask for? At least 3. We want to make sure that this is one of them. So square root of x plus 2. Now, the rest of the points, not only do we want them to be greater than 4, but because it's a square root, what else would make sense? Perfect squares, sure. So what's the next perfect square? And after that, and that should be enough. Square root of 4 is 2 plus 2 is 4. Square root of 9 is 3 plus 2 is 5. And this gives me 6. Now that last one's not going to fit there. That 16, 6 is not going to fit, but we'll just do our best. 4, 4. Now this one does carry a closed point because that 4 is part of that interval. Then 9, 5 is here, and then I ran out of space. So I'll just try to make it look somewhat curvy. But that looks like that. Juancito, what's the domain here? He's using way too many words. Koa, domain. You're the man, Koa. Juan, try to be more like Koa. Why all real numbers? There's no gaps. It's not just because of the arrows. It's because over here where it starts to get like a little sketchy. You know, it's defined, 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 defined. Oh man, I have this open dot here, but right above it, it's a closed dot. So every input is able to give you an output. There are no discontinuities. But how about range? We go from negative infinity up until where? If we're going down from bottom up until 0. At 0, we can't even give you an output, so it's a parentheses. And then now there is a gap where there is no definition. Now, luckily to be a function, you don't have to pass the horizontal line test. Like you can have discontinuities there. So union, and when do we start up again? Bracket or parentheses? Bracket 4, and then all the way up to positive infinity. Fax machine. Kendall, how was your weekend? How many pages did you read? No books? Any questions? Ask now. All right. Yay. I'm not going to say who, but somebody was really worried about you. Sophie's still in the party? Maybe she got lost. Pass that down. All right, example 3 here. We have 3 pieces. We're only being asked to graph, and then this new thing, which we haven't asked yet, we'll get to that when we get there, which is rate of change. Let's graph it first. How would I describe this piece? Constant. Those are going to be fun. You'll love those. Those are the easiest to graph. How would you describe that? Quadratic. How would you describe this? Constant. All right, so let's do with the first one, the constant. The thing with a constant, you don't need any like table or anything because you know it's just going to be a horizontal line. Now you want to make sure you get the endpoint, which is at negative 2. So I'm going to put a point at negative 2, comma 3. But now that point, because negative 2 is not inclusive, it has to be open. So negative 2, comma 3 with an open point. And these are for numbers that are less than 2. So when I draw my line with the arrow, it's going to go that way. That's my first piece. If you want to skip to the last one, just because it's easy, I'm also going to have a point at 2, negative 1. So 2, negative 1 is right here. Those are for numbers greater than or equal to 2, so you are able to fill in the point. And those are for numbers that are greater, so we go to the right. So now we've got to figure out what to do with that middle piece. So x 0.5x squared. You want to make sure you get the endpoints in there. You want to see what's happening at the endpoint. So I'll do negative 2 and 2. For parabolas, do you remember how many points we used to ask for? Well, no, we used to ask for 5, but then that we also were using transformations. We were using reflections. Honestly, I would try to get as many points as possible within the interval. Like, can you think of any numbers here that are in between negative 2 and 2? I would definitely try negative 1, 0, and 1. So negative 2 squared is 4. Times 0.5 means half. Half of 4 is 2. So you get the same thing when you put in a 2. Negative 1 squared is positive 1. Half of that is 0.5. This gives me 0. This gives me 0.5. when I plug those numbers in. Now this first -2, that one had the or equal to sign, so that's gonna, this first -2, 2 is gonna be shaded in. That last 2, 2, which is over here, is not gonna be shaded in. Then -1.5, that you can put a little dot there, 0, 0, little dot, there's a little dot, and then there we go. It's like a happy face. Even though we're not asked there, just for fun, what's the domain? All real numbers, yeah, there's nowhere where this is not defined. This would give you an output everywhere. It would give you some type of an output. Now, what would those outputs be? What's the range? How low and how high does it go? -1 to +3, both with brackets. Actually, wait. No, just kidding. Just kidding. Just kidding. I need more. I need more pieces. There's gaps there. Sorry. This would be it would be -1 by itself with a bracket. Okay. Then union 0 to 2, also with a bracket, because we do have a over here there's a point at the 2. Then union again, and just 3 with a bracket, 3 by itself. Wow, you just got here too. If it reaches that point, if there's actual, if that point is included in the set, if the number is included in the set, it takes a bracket. So it has nothing to do with the fact as to whether or not this is open or closed, but the fact that there are some outputs that give you that number. Here there are some outputs that give you that number. That's why I would take the bracket. All right, so here's this new phrase here that we haven't seen, but you have seen before. You've seen it in Algebra 1. We haven't seen it today, though. What does rate of change mean? What does rate of change mean? Somebody in first period got it. You saw it in Algebra 1. In pre-cal and cal, you're going to see it also. It starts with S and ends with lope. There you go. So for one day only, here's your neighborhood-friendly slope formula. Y1 minus Y2, X1 minus X2. And before you say, oh wait, but I learned it the other way. I learned it was X2 minus X1. I'm about to write 2 points on the board. Who knows what comes first and what comes second? It doesn't make a difference. Now, what we want to do is we want to get these endpoints of the interval. Remember, interval means domain. Those are going to be your x's. So -2 comma something and 0 comma something. And we want to know what outputs we get at those points. We can already see from the table up there, what did we get at -2? Yeah, -2 gave me 2. What did we get at 0? Yeah, sorry, 0. That was from here at 0, 0. So slope is, this is x1, y1, x2, y2. So 2 minus 0 over -2 minus 0, which is 2 over -2, which is -1. That is my rate of change over that interval. Last part. It seems like a lot, but it's not too bad. Sid, evaluate that function at 6. What is the output at 6? Well, 2x is okay. 2x is the function. It's yeah. So when you evaluate it at 6, yeah, it gives you 12. 2 times 6 is 12. Sophie, what would be the function at 0? No. Lydia? Nah. Yash? No, it would not be 0. This 0 fits into this interval. 0 plus 2 is 2. Caleb, what would be the function at -4? That should be the easy one. -4 fits in there. Just 1. So the first piece is a constant function. I would put a point at -2, 1, and it's closed because it has the or equal to sign. Coming to the left. The next piece, how can I describe that next piece? Linear. I would just put the points at the endpoints. What's -2 plus 2? 0. So I'm putting a point at -2, 0, but with an open point. And then when I put in the 3, what's 3 plus 2? 5. So 3, 5, but that one takes a closed point. And then just connect the dots. That's the next piece. The last piece is also linear. I would put at the end point here, and the 2 times 3 is 6, but this is because of the it doesn't have an or equal to sign. 3, 6 is going to be open. Then you could either just pick one more point, like Sid already picked 6. Oh, but it's not gonna fit there. I guess let's just do 5. What's if I were to put a 5 in for x, it'd be 10. So 5, 10, and then connect those dots. But this one takes an arrow. This one goes through. What's the domain here? All real numbers. There is no gap here. All real numbers. How about the range? How low does this go? It goes as low as 0, but there are no gaps. Even though this looks like a gap in here, it isn't, because that piece is defined inside that little that space. So we would go as low as 0, but with a parentheses. When do we reach our first gap in the range? At 5. So we go from 0 to 5, but that 5 is going to take a bracket. Union. When do we start again? At 6 with a parentheses up until positive infinity. And the last question is rate of change. When they give you, these are just intervals. Remember, intervals mean x's. So they want to know what's happening at 0, something, 2, something. And then the next part is 4, something, 6, something. Question, Caroline? Because if I look in this space here, there is nothing in between there, right? But then down here, if I look in this space, there is. It's defined there. You understand what I'm saying? It's weird. With it, it's easier for domain than range. Range gets a little tricky sometimes. All right, what was the output for 0? What was I getting for 0? 0 did give me 2. What was the output for 2? 2, it was 2 plus 2, right, which is 4. What was the output for 4? 8. What was the output for 6? That's the one that Sydney gave me, which was 12. So now that we have all these points, let's do slope. 2 minus 4 over 0 minus 2 is negative 2 over negative 2. My slope is 1. Here, slope is from Algebra 1, 8 minus 12 over 4 minus 6, negative 4 over negative 2, which gives me 2. Any questions? We'll continue tomorrow. And depending, there's no test this week or quizzes, so should work out all right.